All right. Good morning, everyone. Welcome back to Math 154 as always. Week 9, Lecture 1. So past the halfway point. Got our whiteboard with a couple of due dates, 3.4, 4.1. We should already know those, 1021 and 1026 respectively. We are going to knock out 4.2 today, so that will be due on the 28th. We have that Excel 4.1 budget that we talked about a couple classes ago. That's due on the 21st. We have that Canvas quiz. That's a percent-based question that's going to be due on the 26th that we talked about last time. And then we also have a discussion board that we talked about last time. If you want any of those details, please go back and watch the lecture from last time. That's going to be due on the 21st. Remember, that's a discussion board that everyone must participate on, and on any of those, if you don't participate, you get 2 zeros, not just 1. It is a forced participation. And we talked about how everyone can participate by just going to the next year, to the next year, to the next year, and whatnot. All right, so I don't really have too long of an introduction this morning. Like I said, we are going to talk about the midterm coming up in the next couple classes as we get closer to finishing chapter 4. And the midterm is going to be about a week after we finish chapter 4. You've also got your project that you should be working on. Remember, the project is covering the month of November for actually recording your information, but you can go ahead and start building that Excel file now if you'd like to. You can just have a couple of fake numbers in there to make sure your formulas and whatnot are working. But besides that, let's get into this idea of what we call part-to-part and part-to-whole ratios.
Part2Whole ratios. And you will notice that this is another one of those not very long sections. As you can see, this is all the stuff I had in the pre-type notes. I will take an exercise from the guided worksheets and talk about it with y'all. This will be just a discussion, not an assignment. And then from there, we'll get into 4.3. So the reason that 4.2 is a pretty short section is because we have essentially already done this. And you might have said the same thing about 4.1, but we did introduce the new concept of, talking about percentages a lot more. Maybe not necessarily a new concept, but just getting us used to it being a regular piece of our vocabulary and techniques and blah, blah, blah. Part-to-whole ratios doesn't really feel like a different thing because we've been talking about part-to-whole ratios. In fact, the last section, we talked about how a percentage was literally a part-to-whole relationship, but where you scaled the whole to 100. So I'm going to say that one more time. A part-to-whole relationship scale where the whole is scaled to 100 is when you're dealing with things as a percentage. But that's when you're talking about the whole being 100%. You can instead choose to scale the part to 100, but then things get a little weirder. And you also don't have to do a part-to-whole relationship. You can also do a part-to-part relationship. So I feel like this section isn't titled well enough. It should be called part-to-whole and part-to-part ratios. Because I feel like this section more focuses on the part-to-part aspect since it's something that we really hadn't done too much so far, if at all, except maybe a glancing pass. So please note there's a difference between part-to-part and part-to-whole ratios. Part-to-whole is comparing one type of thing to everything, whereas a part-to-part is comparing one type of thing to another type of thing. So for instance, we talked about the percentage of students who are numerate enough to work in a car factory, an auto factory, whatever. So we compared the amount of people who were numerate enough to all the people. That would have been a part-to-whole. But instead what I could have done is said I could compare the people who know enough math to the people who don't know enough math or are not numerate enough. That means the same thing. And that would be a part-to-part because I'd be comparing the people who can to the people who can't. So the people who can, comparing that to the people who can't, that's part-to-part. Part-to-whole would be comparing the people who can to everyone. So again, this would be can to can't for a part-to-part, but the people who can to all people would be part-to-whole. Now, again, I don't necessarily mean every person in the world, just maybe every person in a group that's specified. So an example of a part-to-part versus part-to-whole relationship, without going into that previous example when we have typed up, I've got 4 red balls and 5 red balls. So I've got some marbles or bowling balls or whatever, dodge balls. I'm a bigger fan of dodge balls. So 4 red dodge balls, 5 blue dodge balls. And thus the part-to-part ratio is 4 reds to 5 blues. 4 reds to 5 blues. That's a part-to-part, one part versus another part. And of course, if these were reducible fractions, you would reduce them. Now, why did I choose to go red over blue? Well, personally, because I said red and then I said blue, but you could have, if someone doesn't say you have to do red to blue, or if the logistics don't determine you should do red to blue, you could do blue to red, in which case it would be 5 blue to the 4 red. That is also a part-to-part ratio. It's just a matter of which part you're comparing to which part. Again, in the real world, you may have to determine which one's better. It might not matter which one's better, or you may be just told which way to do it. A part to whole, it's the same. I'm going to use the same numbers above, 4 reds and 5 blues. So I didn't actually tell you how many there were in whole explicitly, but implicitly you can figure it out, because if there's 4 reds and 5 blues, I think it's obvious enough. 4 plus 5 is 9, so there's 9 in total. So the two different ratios you could do as a whole are the reds to wholes or the blues to wholes. So 4 reds to 9 in total, or 5 blues to 9 in total. Now, just like anything dealing with ratios and proportions, you can certainly use a ratio table or a proportion table, whichever you want to call it, they're the same thing. But you might need to actually put in another column, or if you're creating this, you have to know to create this extra column. You need columns for all the parts and a column for the wholes. So what I'm saying here is you need a column for the reds, which would have been 4. You need a column, I don't know why I just had an extra column there. That was a bit more than I needed. Then you have a column for the blues, which we said was 5, and then you have a column for the wholes. So using a proportion table, what you could do is you could say, okay, well, for this, I've got a class, I'm a gym teacher, PE teacher, and for a class of maybe some number of students, I need 4 red dodgeballs and 5 blue dodgeballs. So maybe I need that many for 30 students, because not everybody's going to play dodgeball, or not everybody's going to have a dodgeball all at once. That would just be insanity, right? So 30 students, I'll have 9 dodgeballs, 4 reds and 5 blues. Why the difference? Who knows? Who cares? Not the point of the problem. All right, so if I had a class of 60 students, how many of each would I need if this is going to be a proportional relationship? I always want all these kind of multipliers to hold true. So you could say, okay, well, when you have 30, you could, all right, so if you have your total class, that's why I had that one there. So total students, if I had 30 here, so that has nothing to do with the actual count. I'm just saying, here's another thing that's going to be in proportion with that. So then if I got 2 classes, if I got 60 students, how many do I need? Well, you could set up a proportion using those 4 things, and you could figure out what this x is, because you got 3 corners of numbers. Or you could set up a proportion using these corners, and that would be your unknown, and you could figure out how many blues you would need. Or you could do a proportion table using these as your corners, 3 numbers and a variable, and you could figure out what that x is. Or you could do this with a y equals kx setup if you prefer. Some people will go, well, oh, this went from 30 to 60, so everything doubles. So I'll have 18 dodgeballs in total, I'll have 10 blues, and I'll have 8 reds. Someone who's very observant would catch that. Now, if I said, well, what about if I had 42 students? These numbers would be a lot more difficult to just pick up off the top of my head, but I could do proportion tables and figure out how many dodgeballs I'd need. And I'd probably have some rounding involved there. So we keep coming back to this idea, this proportion table. And again, you don't have to. Y equals kx works. The idea of doubling one and doubling the other works, as long as you've got nice, pretty numbers. But you're going to need to be careful not to misinterpret some things when you end up talking about percentages, which we'll get into in an example. So we'll see this text example in just a few minutes. So be careful not to misinterpret, as we will see in the text example. Well, when I say text example, I mean the activity. And that's on page 161. So note that many homework examples will have numbers on different time scales. So just be careful with that. So if one thing is in hours and another thing is in minutes, convert them to all the same time scale, or just be careful with your units. Again, proportions work even across different units. as long as you're careful to pay attention to your units. And then just one little final detail before we go into that example, and this I think is pretty obvious, but let's say I told you the 4 reds and 5 blues. Well, you can find the whole by just adding the 2 parts. But what if I told you instead that there are 5 blue dodgeballs, and I also told you that there were 9 total? How could I have figured out how many red, as long as we know that there's only 2 types of dodgeballs? Well, it's just an algebraic rearrangement of part plus part as whole. You just take the total, subtract 1 part to get the other. 9 minus 5 is 4. It's pretty simple arithmetic. But if you don't understand that simple arithmetic, you might get stuck a little bit here and there. So I'm just pulling something from my notebook because it's in a funny position. So again, but that's only if you know there's 2 parts. If I tell you there's 5 parts and I only tell you 1 part in the total, you surely can't figure out the other parts because you can only not know one thing. That's a pretty general rule of thumb in math. If you know all but one thing, you can figure out what that missing component is. If you're missing several components, it becomes a much more difficult, if not impossible, problem for us to figure out. All right, so let me minimize this, minimize that. I got my blank one for my work. We'll do that, and we'll do this. Is everything on the screen? Everything looks pretty good. Okay. So again, page 161, page 161, and those of you in the back who can't hear me, page 161. Yes, that's a joke that someone always asks later. So this 4.2 part-to-part ratios, this table involving boys to girls, and then as a whole, so we've got classes where in these courses, the ratio of boys to girls is always 2 to 3. So we're told this is always what happens no matter what. Is this going to be true in the real world? Most likely no. Most likely one semester is going to be completely different from a different semester. One course is going to be different from another course. Maybe this is just a general trend. So if you look at every single course across maybe 20,000 students, maybe it's just pretty consistently 2 to 3. But over time, that's likely to change. Maybe just a month, maybe a year, maybe a decade. But again, for the context of the problem, we're told it's proportional. So for every 2 boys, there's 3 girls, which means if I have 4 boys, there's 6 girls. It means if I have 8 boys, then there are 12 girls. If there's 20 boys, then there's 30 girls. Now, we're going with the idea that we're just going to label boys and girls. So then the students as a whole are 5. Again, just going with the context of this problem. And then, where are we? Sorry, this is kind of small font for me. So it's easy, there we go. Then it can be easy to mistakenly say the boys are 66.7% of the class. Or even worse, 66.7% of the girls are boys. The correct statement uses the size of each part, though. The number of boys is 66.7% of the number of girls. What's going on there? Where is this coming from? How do we figure this out? All right, so I'm going to ignore this row for just a few minutes. But what they have done here is they have scaled the number of girls to 100. So we don't have this number for now. Let's pretend like we didn't see that. So this is what we know. We know it's 2 boys for every 3 girls, and we're just going with the classic boys and girls. So 5 students in total. For every 2 boys, 3 girls, 5 total. So if there were 4 boys, there'd be 6 girls, and there'd be 10 students total. We could keep making more rows because it's a proportion table. 20, 30, 50, 200, 300, 500. Those would all be perfectly the same proportional relationships. So what we're going to start doing is we're going to scale some things to 100. We can scale the boys to 100, we can scale the girls to 100, or we can scale the students to 100. So scaling any category to 100 says that that would be counted as the 100%. So just as a special reminder, scaling any category to 100 makes that category 100%. The new line, of course. Let me hit enter so that doesn't look goofy. There we go. Back Before I do that, let's do one more thing. Remove, enter, perfect. So what they decided to do is they said, well, let's scale the girls to 100. They said, let's have our boys. That was weird. Silly me. We have our boys, we have our girls, and then we have all, or just students, whatever you like. And we said we originally have 2 to 3 relationship, which means 5 in total. For every 2 boys, there's 5 total. For every 3 girls, there's 5 total. And they say, okay, well, let's just start scaling things to 100. So if I put a 100 here, we're calling everything based on the girls. So the girls will be the 100 percentage. And if you were to solve this as a proportion, you can draw your little box right here with 3 corners being numbers, and then this would be our variable. And I'm going to call that variable b. So we go 2 over b equals 3 over 100. Cross multiply, you'll get 200 equals 3b. Divide both sides by 3. And it turns out that 200 divided by 3 is 66.7 if you round to the nearest tenth. So that would be the number of boys. So if there were 100 girls, that says there would be 66.7 boys. Now, yes, we'd probably round that to 67 for context of a small class. If we're talking about tens or hundreds of thousands of students, we would probably use 66.7 because large numbers, we start allowing decimals of people. It's just a thing. So this is where the misstatements come in this window. So someone might say the boys are 66.7% of the class because, oh, we scaled something to 100. So now we're thinking of this as a percentage. So the boys, since that was 66.7, we say the boys make up 66.7% of the class. And that is completely false because we're not comparing the boys to the class. The class was here. We didn't use that. We were comparing the boys to the girls. Now, another misstatement some people might accidentally make. Hold on, there we go. Another misstatement someone might make is that 67.7% of the girls are boys. So they might think that it's just saying that this percentage is based off of that. So 66.7% of boys are girls. Well, I think that's clearly not true. So what is really happening here? So again, we're talking about just comparing the boys to girls, but we're not saying this percentage of boys are girls. We're just talking about the size of the population. That if we're calling the girls 100%, boys would be 66.7% in comparison to that. So the correct statement is the number of boys is 66.7% of the number of girls. So if there were 100 girls, there'd be 66.7 boys. The number of boys would be 66.7% of the number of girls. So again, this last sentence in that summary is extremely important to understand because this 100 was here. Oh, that was weird. Because that 100 was there, not in the all category. We're not saying that the number we got for boys is the percentage of the class. It's the percentage of the value of girls. So it's the boys are 66.7% of the girls. If I do this a different way, let me do this in black now. If I put 100 for the boys, now I can figure out the number of girls. Now you could draw your box around rows 2 and 3, but it's better to do it this way since then you're not using borrowed information. Corner, 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 numbers, variable. So you go 2 over 100. Oops, let me undo all that just so you don't have it stuck. 2 over 100 equals 3 over the number of girls. You'll cross multiply. You'll get 2g equals 300. Divide both sides by 2. Half of 300 is 150. So g is equal to 150. So that says if you call the boys 100, there would be 150 girls. Or the girls are 150% of the size of the boys. So the girls, or the number of girls, is 150% of the number of boys. In other words, if there were 200 boys, you multiply it by 150% to get girls. So you multiply by 1.5 and you'd have 300. Again, nowhere in this statement was anything about all because we didn't use the 100 in the all. So for the third version of this, let's make the 100 in the all. So now we will be thinking about this as a percentage of the total population. It's only when you put the 100 in the total that you're thinking about everything as a total of the population. Now you can solve for boys or girls. Let me just give these different letters since I already wrote B and G, so I'll call them X and Y. And you can make similar proportion tables to find this. So if you want to find X, this is the box you'd be drawing, so 2X, 5, and 100. Or if you wanted to solve for Y, so I'm just going to write that over here. Erase. What's going on? Thank you. Thank you. Thank you. And then if you do it this way, you have 3 over y equals 5 over 100. And remember that there's like 8 or 16 different ways to write out those proportions. I just like writing them in the most obvious way, top over bottom, with left on the right, left on the left, and right on the right. So we get 3 over y equals 5 over 100. I missed one. There we go. So cross multiplying the first one gives you 200 equals 5x. Dividing both sides by 5 will give you 40 is equal to x. Multiply both sides, cross multiply, you get 300 is equal to 5y. Divide both sides by 5, and you get 60 is equal to y. Let me scale back just a little. So that was x was the number of boys, y was the number of girls, both when you scale the population to 100. So now we're thinking about the total population as the 100%. So now these statements would be the number of boys is 40% of the population, of the total number of students, population, however you want to phrase this, and the number of girls is 60% of the total population of students, however you wanted to say that in a nice quantitative way. So the boys make up 40% of the total, the girls make up 60% of the total. You can only make a statement that way when you scale the total to 100. Scaling a part to 100 gives you a way of comparing one part to another. And what's really interesting is, look how drastically different these numbers were. The boys, when you compare them to the girls, as thinking of the girls as a baseline, boys was 66.7% of them. But when you think about the boys as the baseline of 100%, the girls is 150% of them. This demonstrates a very important property that when we think about a percentage of one category versus another, it really matters which one you're calling the baseline. And as we get into the next two sections where we start talking about percentage increases, like a salary increase or your adjustable rate mortgage increasing, if you still have one of those archaic devilish things, which you should get rid of immediately if you can. When we talk about things changing and we start talking about them changing as percentages, it matters which one you're talking about first and second. It matters whether you're basing it off of the first or second value. And that is clearly demonstrated here because that percentage of one versus the other clearly mattered whether we made the boys the 100% or the girls the 100%. And it's usually like this where one is less than 100 and the other is more than 100 in a scenario, as we're seeing here. It doesn't have to be, that's again, just, I'm sorry, not again, but that's just true when we're talking about two parts. If I give you 3 or 4 or 5 parts, then things might work a little differently. All right, so that is, believe it or not, 4.2, and I need to clear my screen. That was from the earlier annotations. This guided activity right here, this is a great one if you want to try it on your own. Because this top row, you have categories, people under 18, 18 to 64, and then 65 and over. So you have your young people, your, let's just say middle-aged people. I know that's someone who's 18 is not middle-aged, just go with it. And then we have our old people. And again, if you don't feel old at 65, please don't take that as offensive. I'm just trying to categorize this in young, medium, and old. That's all I'm trying to do, not based on any particular age barriers. So if you want to know the total here, Well, this would not be a proportion because this is a total, so you just add the parts. So you'd add the parts to get this total. And then they say, all right, well, let's scale the middle-aged, again, no offense meant, in the middle-aged people 100. So you can figure out these two parts based on that scale to 100 by doing proportions. And then you can think of the under 18-year-olds as a percentage of a number of the 18 to 64s, and same thing for the older people. You can do the same thing, scale the 65 and older to 100. They don't do it here, but you could also scale the under 18s to 100. And then finally, they scale everyone to 100. So the last row you see here would be able to say, all right, well, the under 18s are this percentage of the population. The quote middle people are this percent of the population. And the quote old people are this percent of the population. And since that's the only three categories we have, you could actually check that by adding all three, and they should be 100, or only off by like 0.1 because rounding. So maybe try that out. It is literally the same thing as we just did with boys and girls. So try that out on your own. I'm not going to make it an official discussion board. Yeah, so just a good problem to check out. Okay, so I'll leave that in case I need it for later. Let's move on to 4.3. Something I just alluded to mere minutes ago, percent change and difference. So 4.3 and 4.4 are really the same material. We just, in 4.4, approach it with another baseline. So again, 4.3 and 4.4 are pretty much the same material, but the language in 4.4 confuses a lot of people. But let's worry about that when we get there. This is my favorite topic in the course that isn't just pure finance. It's my favorite topic in the course because if you ever get a pay raise, this is how your pay raise is based off of. If your house ever increases in value, this is how it increases based off of. If you're ever trying to talk about your strength gains or weight gains as a percentage, if you're gaining muscle, or weight losses as a percentage, this is what it's based off. There are literally trillions of things in this universe that deal with percent change and total change. Stock market stuff, I see it every day. You could talk about a car losing its fuel efficiency over time, or its engine power, its horsepower over time as a percent change from year to year. You can look at things as a total change from the beginning year to the end year, or you can do this as a year by year scenario. All right, so let's get into it. Let's actually discuss it. Let's learn the formulas that you'll have to memorize per usual. Then when I call these formulas, I also tend to prefer just to call them concepts, because as you know, I call a formula that only has one step a concept. So total change. Total change is the first thing we talk about because it's the easiest thing to talk about. Some people will also call this a dollar change when we're talking about money, or an absolute change. So total change and absolute change, those phrases really mean the same thing. Also, dollar change means the same thing, but again, that's very topic specific. So total change is the difference in the two values, and we mark this as positive if increasing or negative as decreasing. And yes, I know you don't usually write positive numbers with a plus, but quite often we will want to, just to make sure we know it's increasing. In your homework, they may ask you to periodically to do that, so make sure you follow the instructions. When we do guided activities together, or as a discussion board, I would also ask you to write those pluses, again, just for emphasis. So change, the word change means difference. You might go, well, Mr. Beckner, change means some parts of a dollar. Okay, that's another definition of change. Words have different meanings. So when we're saying this definition of change, change means difference. Change means difference. Change means difference. If you've gone through a traditional math class where you've talked about the formula for slope, this is me whispering at you where we will in chapter 5, That is literally just a formula that's a ratio of changes. And people go, oh, it's such a crazy formula to remember. Y2 minus Y1 over X2 minus X1. Yeah, when you think about it in terms of pure memorization, but it's a ratio of changes. Ratio means fraction, change means subtraction. So it's two things being subtracted, one at top and one at bottom. That's actually quite easy as a concept. As a formula, yeah, it's annoying to memorize at first. I get it. That's why we teach you to think quantitatively, to think logically, to put pieces of a puzzle together. All right. So total change is just a difference. Total change is a difference. Total change is a difference. Don't you ever forget that again. When we talk about things as a percent change, sometimes some people will just use the percent symbol. It is the relative difference. So percent change, relative change, percent change with the symbol, those all mean the same thing. So this total change that we talked about before goes with this formula. Total change is new minus old. And it always has to go new minus old, 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 new minus old. Did I annoy you yet? New minus old. Did you forget yet? New minus old. Total change is new minus old. All right, I won't say it again for now. Whereas percent change is the relative difference. And the word relative, if you actually point out some of the words letters, E, you can get rate out of relative. So relative is a rate or a ratio. So what it is, it's the change in comparison to the original. It's the change in comparison to the original. It's the change in comparison to the original. When I say in comparison, I mean as a rate. Percent change is the ratio of the total change, and we're scaling it to the original. We're scaling to the original value. It doesn't make sense to scale to the new value because we're trying to think about the change in comparison to what we used to have, not what we will have. Think about it this way. If you get a salary increase, let's say you make currently $10,000 a year working part-time, and your boss says, I'm going to give you a 50% raise, and maybe it just means you're getting 50% more hours. I don't know. Your new salary is not going to be based on some percentage of the new salary. That would be a redundancy, and it would be impossible to figure out. Your new salary would be based on your old salary. So when you think about that 50% pay increase, that's a percent change based on the original amount that you made. So again, percent changes are based on what happened first. This is critical. This is one of the two most commonly made mistakes with this stuff, is that people scale it to the new, and you're supposed to scale it to the old. So it's a ratio of the difference. Total change is the difference. So some people will say, oh, okay, well, let me just say percent change is equal to the new minus the old. Let me erase that little blip. And then divided by the old. Old, original, those are interchangeable words. And yes, that is the formula as well, but it's just a little bit, it's two steps now instead of one. So if you remember that total change is a difference, percent change is the ratio of total change to original, each of those things is only one step. But please understand that this percent change, since the word percent is in the topic, the answer should be a percentage. But when you do divisions, I don't see a scale to 100 anywhere. We scaled it to the original. So this is not going to be a percentage. It will be a decimal originally that you have to convert to a percentage. In other words, move the decimal right twice, or set it equal to a fraction blank over 100. Because then that would be doing a proportion. You have options. I'm telling you, I love this math because there's so many ways to get something right just based on logic and reasoning, not based on, oh, b squared minus 4ac all over 2a with a square root and blah, 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 blah. Or, you know, the integral of sine is negative cosine plus c. It's not anything that just seems to be pulled out of thin air. These are topics that are constantly relating to each other. So you have got to memorize those, quote, formulas. So before I do the example you see on the screen, let's say that we've got a store, and that store sells 2 apples on Monday and 8 apples on Tuesday. Find the total change marked as increase or decrease. That's important over these days, as well as the percent change. Now, here's the classic mistake that people will do is they'll go, oh, well, 8 divided by 2 is 4, so that was a 400% change. No, that's completely wrong. 8 divided by 2 is 4, scaled to a percentage is 400, but that would just mean that the number of apples sold on Tuesday is 400% of the apples that we sold on Monday. That's going back to the previous section because we're scaling the apples on Monday to the apples on Tuesday. So you do 8 divided by 2, and you have the 100 for the Tuesday, and you'd get 400%. I'm sorry, 100 for the Monday. I said that wrong. That would have been the last section material. This is something completely different. We're different. We're trying to find the change, the total change, the percent change. So the 2 apples on Monday, assuming Monday comes before Tuesday, we're in the same week. This would be the old. The 8 apples on Tuesday would be the new. So your total change is the new minus the old. 8 apples minus 2 apples, which would be 6 apples. So that means we sold 6 more apples on Tuesday. Okay, well, that statement by itself is fine. We sold 6 more apples on Tuesday. But is that a lot or is that a little? Well, some people will say, well, that's a lot because we only sold 2 on Monday, so 6 more apples, that's a significant increase. Okay, yes, selling 6 more apples on Tuesday versus Monday is significant knowing that we only sold 2 apples on Monday. But what if I just sold you, I've got a store, I'll erase this in a minute, but I know there's a store somewhere and they sold 6 more apples on Tuesday. Now I ask you, was that significant? And you might go, well, Mr. Beckner, what kind of store are we talking about here? Are we talking about the corner market? Are we talking about a small little organic grocery store? Are we talking about Kroger or Walmart, these big mega stores that have, thousands of customers each day? Because if we're talking about Kroger selling 6 more apples on Tuesday, that's nothing. Because Monday they probably sold 500 apples, and then on Tuesday they sold 506 apples. So selling 6 more apples in that scenario is not really a significant change. But if we are talking about our little corner store, where we sold 2 apples on Monday because we don't, sell just a lot of fruit. We had a bunch of small things. We sell a little bit of a lot of different things, enough to, get by as a store, whatever. And then maybe we just got a new batch of apples on Tuesday, or maybe somebody came in apple hungry. I don't know. Somebody just got back from the dentist and feeling pretty good about their pearly whites. So, oh man, we sold 6 more apples on Tuesday. That's significant. We probably need to put in a new order now. Blah, 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 blah. So the concept of total change is cool, knowing just the pure difference of one thing versus another thing, new versus old. But percent change scales to the original quantity, so it's a lot easier to think of it in terms of a relative change. So the percent change, which again, we take the total change, which we just got. We didn't have that originally. We take the 6 more apples, which was an increase. That was an increase, by the way. I said more implies increase. So that's a positive 6 apples, and you can write the positive 6 there if you like. And then we divide that by the original number of apples, not the 8 apples, the 2 apples. And when we do that, the apples cancel. 6 divided by 2 is 3, and we get 3. Now, there's no units here. That's pretty common. Percent change is generally going to be unitless because these units will cancel each other out. See, I keep writing my units. The only time I don't write my units is when I write a proportion to cross multiply and solve. That is the only time I ever don't write units in this course. But then we also said the value you get here is a decimal originally. This was not a 3% increase. That doesn't sound right. We went from 2 to 8. That was big. That was a monster increase. 3% is not a monster increase. This is a decimal that we then move its decimal right twice to convert it to a percent, or set 3/1 equal to blank over 100, cross multiply and solve, and you get the same thing. So this was a 300% increase from Monday to Tuesday. That is significant. A 300% increase in sales of anything is absolutely significant. So now if I say, oh, I don't know how many apples we sold, I just know that there was a 300% increase. Now I know whether we were a corner store or a Kroger, that was a big increase. If we were Kroger, we probably went from, say, 200 apples to 800 apples. This corner store went from 2 to 8, though. But either way, both of those would be a 300% increase. Now you're thinking, Mr. Beckner, why isn't it 400%? Because you didn't hear me earlier. 400% would be just comparing the two. We're talking about the change, and the change disregards what we originally had. That's why we subtracted it off. So subtracting this 2 off is where that other 100% essentially went. We don't include that because let's say we started at 2 and we ended at 2. That would be a 0% change because it's a 0 change. We didn't sell any more apples. But if you just did 2 divided by 2, you'd say, oh, that's 100%. Well, yes, the apples we sell on Tuesday is 100% of the apples we sold on Monday, but that's not a 100% increase. So you have got to understand this. Moving forward becomes a big issue. You must be able to decipher between a regular percent and a percent change. So far until now, we'd only been talking about percentages where we were scaling one thing to another, dividing one thing by another, scaling it to 100, things like that. Now we're talking about this new word, change, and this word change is going to be common in Chapter 5, Chapter 6, Chapter 8, and Chapter 9. This is never going away for this entire course. I guarantee that. So go ahead and put in your 3 to 6 hours this week and get this understood immediately. Again, 8 divided by 2 is 4. Oh, that's 400%. That statement would be the number of apples sold on Tuesday was 400% of the number of apples sold on Monday. Didn't ask that though. I said, what was the percent increase? So we cut out the original, then divided by the original, and that gives us the change, the increase. So the total change or absolute change was we sold 6 more apples. The percent change, which scales it to the original, says we sold 2 more apples. So if you did this for a Kroger that sold 500 apples on Monday and 505 apples on Tuesday, that percent change would be just insignificant practically. It would be 1%, in fact. So if you had 500 apples on Monday and then 505 apples Tuesday, the total change would still be 5. You do 505 apples minus 500 apples, which is 5 apples, literally the same exact change, total change that is. But the percent change would be that 5 apple increase divided by the original 500 apples. 5 over 500 is 0.01 or 1/100th. Scaling that to a percent becomes 1%. Increase. So your corner store that went from 2 to 8, why did I say the same change? I was supposed to do 506. Oh well, you get the idea. It was just one off. Oh boy. Close enough. 506. So an increase of 6 apples. And then we do 6 divided by 500. And that's close enough. So 6 divided by 500 is 0.012, so it's a 1.2% increase. So the total change of the Kroger apple sales in these two scenarios, 506, I just changed it so that they'd be the same. It still sold 6 more apples on Tuesday, but because they sold so many Monday, the percent change feels almost significant. It was only 1.2% more, whereas this corner store sold 300% more. Big difference. All right, let's try out another example like that. Last year, Mr. Beckner had 20 students in his 11 a.m. Tuesday, Thursday class. This is just arbitrary. This year, he has 30. What is the total and percent change? So you've got to have organized which one's the new and which one is the old. Which one comes first in time? Well, last year, 20, that's the old. Oh, 11 a.m., that's the new, right? No, 11 a.m. is just a label. This year he has 30, that's the new. So our total change, or absolute change, remember those words are sorry for the pun, changeable. That's new minus old, not old minus new minus old. 30 students minus 20 students, which is 10 students. Do not just write 30 minus 20. That's a horrible habit. You will not be a good quantitative reasoning student doing that. Now, that's a positive number, so it's an increase. And I think that it's obvious that it's an increase. We went from 20 to 30, it went up. So this year there are 10 more students. That's what we can say. Now, 10 more students, is that a lot? Is that a little? Well, to understand if it's a lot or a little, you have to think about it scaled to the original amount. If I'm talking about the total population of TCC, which is in the thousands, a 10-student increase is insignificant. But if I'm talking about one class, a 10-student increase seems significant. So it's all about the original population's size in comparison to the change's size. That's what percent change does for us. So that's a ratio. So total change is a difference, percent change is a ratio. And this is the ratio of total change, which was the positive 10 students. That was the increase, divided by the original number of students. Again, percent change is always scaled to the old, not the new. And the old was the original, the 20 students. 10 divided by 20 is a half, 0.5, a half, however you want to write it. The students as units cancel. So we get 0.5. Converting that to a percentage, though, is 50%. And that's an increase because it's positive. So we can say that Mr. Beckner's class size increased by 50%. That is significant. If I just tell you a class has 10 more students, and I ask, is that significant? You can go, well, I don't know. Are we talking about a normal class with 20 or 30 students? Or are we talking about one of those lecture hall classes with 200 or 300 students? Because a teacher who normally teaches 20 students and gets 10 more is going to feel that effect. A teacher who teaches 200 students usually and now has 210 isn't going to really feel that effect. Also, someone who's teaching 200 students, they either have less classes that they teach or they have assistants to help with grading, things like that. That's usually more of a university issue than a community college issue, though, but you get the idea. All right, so this is example 1. That's weird. I had an example 2 typed up and it's not up here. That's all right. Example 2. Same kind of concept. Last semester, Beckner had 30 students. This semester, he has 9. Blah, 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 blah. What's the total and percent change? Okay. So last year he had 30, I had 30. I sound crazy when I say it that way, don't I? This semester, we've got 9 students in a particular class. 11 a.m. Tuesday, Thursday, 7 p.m. Monday night, whatever, who cares what particular time slot it is. So our total change, well, the old was the 30. And you have to be careful. They may tell you these in opposite orders. I could certainly tell you the new thing and then the old thing. I could say this semester I've got 9, last semester I had 30. So don't just think old comes first, new comes second. Pay attention to the details. Read. Total change is the difference of these. Old minus new, correct? It's just always the bigger minus the smaller. Nope. That is completely wrong. It's always new minus old. So we got to do 9 students minus 30 students, which is negative 21 students, which says it's a decrease. So the class size decreased by 21 students. So the number of students decreased by 21. Notice I don't say they decreased by negative 21. That would be a double negative. Decreased implies negative. Some people might say, well, can I say increased by negative 21? I mean, technically, yes, but that's extremely confusing. Please don't ever do it. It only works on a technical level. A math person is going to understand you, but average Joe on the street is not going to understand you. There's our total change. So is 21 students a big drop, a little drop? I don't know unless I think about this in terms of the original population. So let's look at this as a percent change. And that's where we take the total change that we just got of negative 21 students, and we're scaling it or dividing it by the original, which was 30 students. The students will cancel in terms of units. 21 divided by 30 as a fraction reduces to 7/10, so that's negative 7 over 10, which would be negative 0.7 as a decimal, which is negative 70% as a percentage. So that's a 70% decrease in student size and class size. Number of students, however you want to say it. Yes, I wrote 2 I's there. Let me just erase one. There we go. So 21 students might not sound like a significant number to you because you're like, oh, are we talking about all of TCC? Are we talking about a lecture hall? Are we talking about a regular class? Well, we're talking about a regular class of 30 students previously. That's a 70% drop. Ooh, that class is hurting. That class might not run. Kind of traditional for classes to be canceled if there's less than 10 students. Not always. That's just kind of the average. And then that throws off schedules. And it's a lot of fun. And one of the biggest issues is students not signing up for classes on time. I'm pointing at lots of people in this class as well as other classes. That's just the TCC way. People sign up late, they get classes canceled, they change people's lives. And that is a fact. So next semester when you're signing up for classes, please do it early. Please don't affect people's lives in that manner. All right. Example 3, again, just kind of not sure where my 2 examples went. I think I have another version of this file somewhere. So for example 3, what we are going to do is swap the order of example 1 occurrences. Analyze. 1 in. There we go. I spelled it right. So we're going to go back to example 1. Let's just pull back a little. Example 1. But we're going to swap the order of the occurrences. What I mean by that is instead of having 20 students, then 30 students, let's say I had 30 students, then 20 students. So now we're going to say 30 students is the old, and 20 students is the new. So I'm just saying, I'm pretending like the scenario flip-flopped. I had 30 students, and then I dropped to 20 students. Okay, so the total change, which I'm just going to mess up for a second. Total change, TC total change, is the new minus the old, which would be 20 students minus 30 students. And that would be negative 10 students. So that would be a decrease now. So the total change of negative 10 students is very similar to the previous total change of positive 10 students. It's just that it's a decrease instead of an increase. It's just positive instead of negative. So the total change, when you swap an order, only matters in sign. The magnitude of the number, the 10 that is actually the same. But the plus or the minus absolutely makes a difference. If you do it backwards, if you do it wrong, you're still going to be wrong. But at least you get the idea that it was a 10 student change. You just might say it went up when it actually went down. But here's where things get interesting. The percent change, scaling the total change of negative 10 students to the original, which is now the 20 students. I'm sorry, which was now the 30 students originally. I was looking at that wrong because of the spacing. 30 students originally. The students cancel. 10, 30 turns into 1/3, so that's negative 1/3, which is 0.33333, which is a percentage, is 33 point and negative still, 33.3%. There we go. So that's a 33.3% decrease in class size. Look at this number. So the total change was basically the same. It's just one was positive, one was negative. But compare the percent changes. When we go from 30 to 20, it's a 33% decrease. But when we go from 20 to 30, it's a 50% increase. So yes, there's still increase versus decrease. That makes sense. But what some people might think is that the percent number should be the same. If one's 50%, the other's 50%, and it's not. And this is exactly the same idea as when we were dealing with that boy-girl problem, because we're thinking in terms of comparing to one particular part, essentially. So old is like a part. It wouldn't make any sense to combine old and new to make a total, but we can still think of old and new as a part and another part. So when your old is a smaller value, that percent increase feels like a bigger change. When your old is a larger value, that percent change feels smaller. So the bigger the old gets, the smaller the percent change tends to be. And if you were to swap these two things, the same can be said of this 30 versus 9. We went from 30 to 9 and it was a 70% decrease. If we go from 9 to 30, that's going to end up being a really large increase. The difference is still 21, which will be doing 21 divided by 9 and converting it to a percent, which is 233% increase. So going from 30 to 9 is a 70% decrease. Going from 9 to 30 is a 233.3% increase. That feels significantly different. And that idea right there is what a lot of people deal with in stocks. So you might say, oh, okay, we went from a stock price of 2 to 8, 300% increase from 8 to 2, that would be a 75% decrease. It's the same change up or down, but as a percentage, it feels drastically different. And when you start talking about stock markets and compounding interest, interests, those effects are really felt. You can't even have like a 200% decrease. That would be impossible because it would put you into the negatives. You could have a 200% increase, and that would definitely bump you up significantly. Pardon me. In fact, I'm not done. Wrong button there. There we go. All right, so next up, what we're going to talk about is the arrow notation from the text. You will probably never see this anywhere in the real world. This is something that our textbook author adapted. You will see it in the homework. You'll see it in the guided worksheets. If you're actually reading the text like you're supposed to do, I'm wagging my finger at you, then you'll see it there as well. But you're probably not going to see this particular notation in the news or in some random article or in your buddy's other homework for another finance class or something like that. This is just very specific. So what this looks like is you have an old value with units. You've got this kind of long arrow pointing at something else, and it points to the new value. Above it is the total change, and below it is the percent change. This is not a fraction. This is not a fraction. This is not a fraction. This is not a formula. This is not a times. This is just a placement of 4 values that, again, you will probably never see outside of this course. Quite honestly, because of that, I wish I didn't have to teach it, but I can't remove it from the homework, so I'm stuck with it. It's a cool notation. It's fine, but again, I've never seen this anywhere else. So again, just understand that this is something you'll learn for the course, but don't expect to see it anywhere else. It's just a way of compiling information together. Some other person could, have some little box and they go old, new, total change, new change, or sorry, new, old, new, total change, percent change. I was looking at the word new there. That was on me. But the problem doing it this way is that you might think, oh, this is a proportion. No, it's not. It's not a proportion. Don't think of it that way, which is why this textbook does not do it that way. Just because you see a table of numbers doesn't make it proportional. You have to be told it's proportional or rationalize that it's proportional. So again, you'll have the original value on the left, and it'll be pointing at the new value. The total change may be up here, or you may have to find it, and that would be up here with a plus or a minus. And then the percent change would be on the bottom. Now, they might not give you these two numbers. They may give you the old and the new, and you have to find them. You may have to find this, and you may have to find that. Or what they might do is maybe they give you the old and the total change, but they don't give you the new and they don't give you the percent change. There's actually a way to figure that out. If we know the old is 10 and the total change is a plus 20, well, the new is 30 because you just take the old and add the change. Or if I said the old was 25, it's not going to work writing it this way. If I said the old was 25 and the change was 10, then that would, and plus 10, that would make the new 35. Or if I said that the change was minus 10, that would make the new 15. But the cool thing is, I don't have to give you the old and the change. I can give you the new. I said eraser, you silly program. Thank you. I could give you the total change in the new and ask you to figure out the old, but it works backwards. If we know the new is 15 and it dropped 10, that means whatever this was, you're subtracting 10 to get 15. It's kind of like an algebra problem. That means to go backwards, you have to add it. 15 plus 10 would give you 25. And if you don't trust that, 25 minus 10 is 15. Or I could tell you that the total change was up 10. If we're at 15 now, that means we went up 10 to get there. That doesn't make the old 25. You don't add 10, you would subtract it, and that makes the old have to be 5. Because 5 plus 10 is 15. So you subtract to get the old. 15 minus 10 is 5. And literally, that's just because it's the old plus the total change is equal to the new. If you algebraically rearrange it, that says that the old is equal to the new minus the total change. You just subtract total change on both sides. Conversely, I can also instead give you maybe the percent change and the old, and you could figure out the other two things based on that, but I'm not going to do that math yet because we haven't done enough to figure it out yet. So this is your arrow notation from your textbook. So if I wanted to go back to the previous problems and write it in this notation, example 1, let's go back to example 1. We said we went from 20 students to 30 students. The 20 was the old, the 30 is the new. The 20 is the old, the 30 is the new. So what we originally have is 20 students pointing at 30 students, and we don't know what the total change is, and we don't know what the percent change is. Now, when we did our math, we got that the total change was an increase of 10 students. So what you can then go back and do is erase the top portion because that's where total change is. Don't put it in the bottom. That would be wrong because total change goes in the top. So you'd put your plus 10 students here, and then you can do your math to figure out the bottom, which is the percent change. So your math, which was, we already did, and we got the percent change, 10 divided by 20 was a 50%. increase, so plus 50%. Again, that's just using this different notation that will not be seen probably anywhere outside of this course. I'm sorry for that, but I will adhere to the course materials, naturally speaking. Let's see. I think we have just enough time to do the example on page 167, 168, and then we'll call it a day. 167, 168, 24, 28. Here we go. I'm gonna do all, no, I'm not. No, I'm not. I don't like it that way. Just go down to here. Compute the total and percent change for the number of all households from 2016 to 2017 by drawing the arrow diagram below. So all four of these are blank. These numbers are in thousands. So I don't have time for you to super analyze this thing, but you would have to pick up overall on this that, all these numbers are in thousands, which means this 126,224 is not saying there's 126,000 households. It's saying there's 126,000 households, which means there's really 3 more zeros after that, which really means there's 126 million households and some change. But these numbers are all going to be in thousands, so we're not going to think about it that way. So they say blah, blah, blah by doing the number of households from 2016 to 2017. Well, here's our 2016 column. They have median incomes. We're not going to be talking about that at all. Margin of error, we're not talking about that at all. Same for these two columns here. We're only going to be talking about this column and this column. But we just got to extract one number out of all of those, and it's the number of all households. Well, if you look at all these categories, they're broken down by male households, no wife, male householder, based on age, based on ethnicity. Right here, household, all households. So these are the numbers we need, the 126,224 and the 127,586. So that's what goes there. So we have oops, I'm on highlighter. That's silly. 126,224 pointing at 127,586. That's our old and our new, 2016, 2017. Then we can find our total change and percent change by subtracting and then doing a ratio. So we go down here and do our work. Our total change is the difference of those, 127,586 minus 126,224. And if you do that math, again, I'm running short on time, so I'm not pulling out a calculator. 1362. That was an increase. And these were in people. Sorry, these were households in thousands. So households, H, and then H for households in thousands. All of those were in thousands. So that's what would go here. So that's the plus 1362 households in thousands. There was an increase of 1,362,000 households, aka 1,362,000 households over 1 year. The percent change, so is that a lot or a little? Let's think about this relative to how many we previously had. So we take the total change and divide it by the original. The total change being that plus 1362 households in thousands. And let's divide that by, basically we're scaling it to the original, which was the 126,224 households in thousands. And again, I'm going to ask you to plug this into your calculator to show this, but you'll get something like 0.0108, and that's a positive number. So when you turn that into a percentage, you'll get 1.08%. That's an increase. It's not thousands of households, that's just a percent increase. So that's the number that goes on the bottom, 1.08 with a plus sign to be technical, percentage. So yes, 1,362,000 households sounds like a big increase, but when you scale it to how many we already had, it's only a 1% increase. That's not a lot. There is a question 3. We don't have time for that. We're going to call it a day there. I believe if you want to try those answers out, if you want to try those problems out, that is to say, that in order, the 5% changes are 3.3%, 2.6%, negative 0.2%, negative 2.2%, and positive 3.7%. So that's based on the 5 different races, which were white, white non-Hispanic, Black, Asian, and then Hispanic. And then the largest percent change up there was the 3.7, which would have been the Hispanic. So again, there's the answers for that third one that you can try out on your own, which I highly encourage you to do. It would be excellent practice. You are simply just looking at these categories. So for the white category, you'd be doing this number versus this number, et cetera, et cetera. Okay, so we'll call it a day there. We have not finished this section. Oops, I need to clear screen. Then I can do that. So we have not finished this section quite yet. We will finish it next time.
So yeah, like I was saying, we will definitely finish it next time. But for now, we know what we have due on the horizon. Like I said, 3.4, then 4.1 and 4.2. We have due dates for my math lab homeworks, the Excel budget homework, the Canvas percent quiz, and the discussion board. So we'll continue our journey with 4.3 next time. And then it's going to be about another class and a half, and we'll finish 4.3 and 4.4 after that, and we'll be ready for that midterm. Like I said, your review materials will be up soon. I should have them available this week sooner than later. As always, if you have any questions, please shoot me an email. Besides that, stay on top of your work, keep studying hard, keep working hard, and we'll see you next time. Take care, everybody.